Okay, so thank you for having me. Yes, my name's James. I work as the tech lead of both Play Framework and Lagom, and Lagom is a new microservices framework that we're going to see a bit of tonight, but actually tonight is not just about Lagom. It's really about architecting microservices. So it applies to a much broader scope of things that you might do, not just one technology. Of course, Lagom's a very good way to do it, which is why we wrote it. So let's get on to what we're going to look at tonight. We're going to first look at tonight what is asynchronous communication. Asynchronous communication is a very broad term which can mean a lot of different things, but I have a specific definition of it that I want to talk about. We're going to compare asynchronous and synchronous architectures, how they perform together, how they might be better than one, might be better than the other. And finally, we're going to look at asynchronous communication in practice. This is where you get to see some of the concepts that I'm talking about tonight applied in Lagom and can be applied to any application. So asynchronous communication, what is it? So the first thing that I want to say about it is that I'm not talking about asynchronous I/O. Asynchronous I/O, sure, is a form of asynchronous communication if you define it very broadly, but I'm more referring to communication between services. So asynchronous I/O is good, okay? Just because I'm not talking about asynchronous I/O doesn't mean it's bad. In fact, Lagom uses asynchronous I/O at a very fundamental level, but it's not what this presentation is about. So just by way of contrast, asynchronous I/O, it means don't consume threads while waiting for things to happen. So here's some code in Java 8. We have here something, we're making a request. That request returns a future of a response or a completion stage. For those of you that haven't come across completion stage before, it's Java's in a way that only Java can do, very long way of saying future or promise. You might have come across futures in Scala or promises in JavaScript. It's a different thing from Java util concurrent future. But it represents a value that is not available yet. It's going to be available sometime in the future. So if we want to do something to this response, it's not available yet. We can't do it. Instead, what we do is we attach a callback to it. And so you can see when I want to decode this response that I've got into some sort of model object, my model. I attach this callback using the thenApply method, which is another Java way of saying map. And that callback won't be executed immediately because the value is not there. After attaching that callback, the thread that's doing this will go and return to the thread pool or go and do something else. And then when the value of the response of the future is redeemed, a thread will be pulled out of a thread pool somewhere and will execute that decode function. So asynchronous I/O is about not blocking threads. Asynchronous communication, in contrast, is about not blocking requests. And what do I mean by that? I mean if a service is processing a request, it should not be blocked on another service having to process another request in order to return its response. So let's have a look at what this means in practice. So we've got a user. User's happy. It's good when the user starts off happy. User makes a request to service A. I'm using the bidirectional arrow there to say that it's synchronous communication. So you have a request going one way and a response going the other. Now, service A actually doesn't have all the data it needs to be able to to fulfill this request that has been made on it. So it has to call out to, it might have to call out to service B, making a synchronous request. So the request goes into A, and then another request goes to B. It processes something and sends a response back to A, and then A can send the response. We might have more. B might need to talk to C during its processing, C might need to talk to D, A might have to go to multiple systems, and E might have to go to D as well. And as long as everything is happy here, as long as all these systems are running and performant and working, then our user will remain happy. They'll get their response. But what happens if service D blows up? Spontaneous server combustion. Well, service C and E there, which depend on it, they're still running. Okay, these are different servers. They're different different services, probably running on different physical machines. There's no reason why, just because service D has failed, that they should also fail. If they're using asynchronous I/O, then they're probably, any requests that are building up on them, they're probably going to be able to manage fine because they're not going to run out of threads. However, the thing is that service C needed to make a request on service D in order to return its own response. So it can no longer do that. So it's going to return an error too. So service C and E, they may as well be down. They just appear to be down as well. Similarly, B and A, they're effectively down. I mean, sure, they're actually running, they can receive a request, but they're not going to be able to send their responses because they depend on these systems downstream that aren't able to send responses. And so consequently, our user isn't happy because they get an error. So synchronous communication, failure bubbles back up the synchronous communication pathways. So we saw that as you communicate synchronously along one direction, back the other direction, the failure goes. Not only that, but slow response times bubble back up. If service C, for example, was slow at processing the response, maybe it was a bit overloaded, its database was slow, whatever reason, that's going to impact how the maximum speed that A can return its response because it's dependent on that service. If you really embrace synchronous communication, you may end up in a situation where some services will be needed by everything. A typical example of this is, let's say you've got an authorization service. So in a social network, you might have a service that manages friendship relationships. And I can only view your post if I'm a friend with you. I can only comment on a post if I'm a friend. I can only like a post if I'm a friend. And so it turns out every single action that happens with the system, it needs to go to this friend service to check this friendship relationship. And so what that means, first of all, the friendship service there would be a bottleneck to load. If it can't, if the whole system is only going to be able to respond and handle as much load as it can handle, and it's also going to be a single point of failure. If it goes down, everything's going to go down. I can no longer like things, post on things, even view things, because it's always being used to check these authorization assertions. And often in a situation where you really embrace synchronous communication, you'll have a situation where the whole system needs to be up simply to serve any request. And when you've got a system that looks like this, what you've really got is something that looks no different and behaves no differently to a monolith. So let's say you've taken your monolith and you've broken it up into microservices, or you might have started a new project and you decided we're going to go to microservices, not a monolith. If you've used synchronous communication everywhere, sure, your code bases might be independent, they might be able to be deployed independently, they might be able to use different technologies, but when it comes to how they behave, they're looking no different from a monolith. So how does asynchronous communication help this? We've got our user makes a request on service A, and service A returns the response, and that's all that's needed. Doesn't matter if anything else is down because service A is there. But hang on, didn't we say that service A doesn't have everything that it needs to serve the request? It needs. So we might have a service over here, service D, and some things happen. It's responding to some sort of external events coming in, and when it receives those events, it's going to push them asynchronously to services C and E. And likewise, C and E are going to push to B and B to A. And so A is going to be presented with all the data it needs from service D, C, E and B via these asynchronous pathways. So that it can always have everything it needs in order to respond to the user. But what happens now when service D goes down? Well, service C and E, they don't actually ever need to call directly onto service D. They're still up, okay? If they are handling synchronous requests themselves, they're fine because they have everything they need. Likewise, service B is still up, and service A is still able to respond to that request. So with asynchronous communication, failure stops at the failed component. Slow response times likewise stop at the slow component. I mean, if service C was slow responding to the events that it was receiving, well, sure, it might take a while then for its events to get through, but service B isn't going to be slowed down, and service A is not going to be slowed down either. It's still going to be able to respond just as fast to the request that it gets. We removed the bottlenecks and single points of failure, so that service D doesn't matter if it goes down to the other services. Consistency may lag, and this is the big problem, because now if like let's say service C goes down, the events pushed by service D are not going to go through that and not eventually make it to the front. But we can use some eventual consistency patterns to be able to address that, and we're going to spend a lot of time looking at that this evening. But the big point here is that the components are isolated. The reason why we do microservices is to isolate the components from each other. We want to create boundaries between them, boundaries for technology, boundaries for deployment and organisational boundaries, but also boundaries for scaling, boundaries for load, boundaries for failure, so that our system can behave and be resilient to these things that happen. So what does this have to do with REST? Okay, so the talk's titled Rethinking REST. I should first point out that when I say REST, there are certain people, and I don't come across them that often, but they certainly do exist, that want very strongly to point out that REST is bigger than just HTTP. And that's true in the original paper that was written about REST. But when you say REST to people today, 99% of developers hear HTTP and JSON or maybe XML. So when I say REST, I'm referring to what 99% of people understand it to mean, which is HTTP. So REST in that context is a synchronous messaging protocol. So the client sends a request and the server sends a response. It can be used to do asynchronous messaging. Okay, any synchronous messaging protocol can still be used to do asynchronous messaging. And HTTP actually has built into the protocol a way to express that semantically, the 204 no content response. So if you send a message to a server via HTTP, it can specifically say, hey, I've got nothing back for you. And that's asynchronous messaging. If we were when we did our code before where we made that request and we got our completion stage of a response back, if we were doing asynchronous messaging there using HTTP, we would simply do nothing with that completion stage. We'd just let it do whatever let it be redeemed or not redeemed or whatever. So REST is not really the problem. This is not a presentation about how you all need to stop using REST. There are plenty of good places where REST can and should be used, especially at the entry points into the system where a browser's going into the system, but even internally between services, there are plenty of good places where REST can still be used. So I've written a social network. It's fairly small at the moment, only has 2 users, but it is one day going to overtake Twitter. Trust me on that. Now, in the first version of this social network, it was a monolith. Okay, I just wanted to get things done as quickly as possible. The social network, by the way, is called Chirper, and so I had this monolith called Chirper, and then I went to a conference and I went to a presentation, and the presentation said that monoliths are bad. And so, oh no, I've got this bad monolith, and so I had to go and convert it to microservices. So I just want to say now, this talk isn't about why you should move to microservices. There are plenty of resources out there that you can, talks that you can go to. There are plenty of blog posts. I'm not really talking about why to go to microservices. I'm just talking more about how this evening. So we're just going to assume that whenever we have a monolith, we want to go to microservices. So this is a rough diagram of what my monolith looked like. And you can see I had 3 components in there. It was a Spring app. They were wired together by Spring. So I had this friend service component, chirp service, like service. Chirp service needs the friend service because when you go and get a list of chirps for the users that you follow, you need to get it needed to get the list of friends. The chirp service needs the like service because when it returns a chirp, it wants to return in that chirp a count of the people who would like it, so that could be kind of rendered on the screen. And the like service needed the friend service because it needs to check that I'm friends with someone before they can like it. So the first step to converting this to microservices is get rid of the monolith. So I did that, but then we've got these raw components out there that need to live somewhere, so let's turn them into their own microservices. So we've got friend service microservice, chirp microservice, like microservice. And then I've got all these things that used to be method calls. So these were all in the same JVM before, but now they're running on different servers. They can't just be method calls. What am I going to do with these communication pathways? Well, let's just replace them with REST. Easy. And so I've converted my system to microservices, and microservices starts delivering everything that it promises, and Chirper becomes really popular. And so after a little while, the number of users increases and the friend service starts getting a bit overwhelmed, and it crashes. So friend service stopped working, but it's microservices. So okay, that part of the application doesn't work, but I still got the chirp service and like service, but because they're synchronously calling the friend service, they're effectively down. And so effectively my whole system is down, and the user's not happy, and if a user can't access their social network, well, we know what happens. So when moving from a monolith to microservices, the problem is not REST. The problem is that REST is our go-to. It's the way we use REST, the way we say, well, here we've got some method calls, and this system needs something from that system, so let's just use REST to get it. So when we move to microservices, we need to make sure that we don't just do a one-to-one service interface replacement. We really need to rethink our architecture and design for an asynchronous architecture. So what does this look like in practice? Distributed systems and doing asynchronous communication is a huge topic. There's no way that I could cover every single technique and practice that you might use in order to replace synchronous communication pathways with asynchronous communication. But I will look at two methods this evening. So the first method that I'm going to look at is called denormalize and push data, and that's the method that we saw. Well, that would be what you do if we were doing it the way with a diagram before, with A talking to B, talking to C, talking to D. Another approach that I'll cover just a little bit is communicating through the client. This actually isn't asynchronous; it's more not synchronous. So denormalize and push. If you've ever used a relational database, you'll probably know a bit about normalization. A normalized data schema has a number of properties, and one of those properties is that data only appears, like any piece of data will only appear once somewhere in your database. You won't have it repeated multiple times. You'll have references between the data that are enforced to ensure that you don't have stale references and things like that as well. When you denormalize and push, the idea is that services will store all the data that they need. And what this might mean is duplicating some of that data. So this is denormalizing it, because a normalized system would have the data only once, but if you're replicating it, then if you're duplicating it, then you've just denormalized. Because of this, consistency needs to be addressed. So the data can get out of sync, especially in the happy case, things might work pretty well, but if something goes down, if something gets overloaded, then this data is, then you will have problems where data is going to get out of sync. You ask one service a question, ask another service the same question, and they give you different answers. One approach that we're going to look at quite in detail this evening to solve this is to use at least once messaging and idempotency. And if you don't know what idempotency is, the idea is you can have the same operation can be performed multiple times on your data, and the state will stay the same regardless of whether it happens once or multiple times. So I mentioned before that the chirp service had to call into the like service to get the count of likes. So this is currently implemented like this. The user goes and gets the chirps, and then the chirp service goes and gets the likes for the chirps, and then returns the chirps with the likes to the user. And so we know if that means if the like service goes down, the chirp service isn't going to be able to return the likes back to the chirps back to the user. So let's get rid of that synchronous communication pathway there, and we'll replace it with an asynchronous communication. What we're actually going to do is every time the likes, somebody likes something, we'll send a count of likes for that chirp to the chirp service, and it can respond to that and store that count of likes for the chirp. So now when the like service goes down, the chirp service is still going to be able to respond to the requests coming into it. So now we'll get into the demo. Chirper has been implemented using Lagom. It's actually a sample app that you can get from the Lagom repository, so you can go and try this out yourself. Lagom is a microservices framework for the JVM. Now the word Lagom is a Swedish word. Don't listen to my pronunciation of it because I'm not Swedish. You'll get it very wrong if you try to replicate my pronunciation. But what it means is just right or sufficient. And it's more than just a word meaning just right or sufficient to them. To the Swedes. It's more of a cultural thing, a way of life, or a way of just having things that are just the right size, not too big, not too small. And so when we're coming up with a name for Lagom, one problem with the word microservices is that it's kind of like services with micro. So micro is the feature word there, which means very small. And people have often taken this too far, and they say you should make sure that your services are as small as possible, and the smaller, the better the system that you're writing. But of course, that's not what microservices is about. Microservices are about having the right boundaries between the services so that they can implement the requirements that they have, whether it's transactional requirements or scaling requirements or resiliency requirements. The service should be sized to be the right size to meet your isolation needs. So Largom fit that really well. It has first-class support for asynchronous messaging, and that's obviously going to help us a lot this evening. It also provides a high productivity development environment. So if you've used Play before, you'll know that when you change some code in Play and you hit refresh on the browser, Play will pick up that change and reload your app, and you'll see it immediately. With Largom, it's doing that not just for one service, but it will run all of your services, and you make a change, and it will reload all of your services that depend on that code change. And finally, it guides you all the way to production. So starting with one of the complex things about microservices is that you're now not just deploying one system, you're deploying many systems. And you have to manage the configuration of those systems, how they talk to each other, how they know about each other, where their databases is, how communication from the outside world gets in. And Largom gives you that through the use of Lightbend Conductor. Currently there's only a Java API. We found when talking to our customers that the questions that our Java customers were asking us were very often about, well, how do I do microservices? How do I get started? What are the best practices? Whereas our Scala customers didn't tend to be asking those questions so much. And so we decided, well, for the first iteration, we'll just implement the Java API, we'll get some feedback, we'll understand whether it's meeting people's requirements or not, and then we'll release a Scala API. We've started working on the Scala API already, and if you go to issue number 1 in the Largom GitHub repository, you'll see it's add a Scala API. And so it's the first thing we're pretty much doing after releasing after we make a general availability release. So let's get into this demo. So here I have my terminal. I've started SBTs, so Largom uses SBT as a build tool and development environment. And I'm going to run this command run all. So when I run all, the first thing that you see happening there is it's going to start a Cassandra server. So Largom actually runs your database for you. You don't need to set that up. It's also running a service locator and gateway. The service locator is how services find each other. The gateway is how requests from the outside, for example, from a browser, will get to the services. And then it's starting each of my services. You can see they're all running on different ports. I don't need to worry about what port they're running on because the gateway knows what port they're running on and will route the requests accordingly. So let's try it out. So here I am inside Chirper. I can write a post. I can view likes. I'm logged in as Bob at the moment. I can like something. I can unlike something. You can see that that summary of likes there that the Chirp service has to get from the like service. And so it's all working, it's all good. I won't show you that many other features because you'll very quickly see that it's really not a very featureful social network. So going to beat Twitter someday. So what happens if our like service goes down? So you can see here, I'm not going to go into this part in too much details, but this is where we actually get the chirp stream. It's using Akka streams here. We've got some recent chirps which we've loaded from the database, and then we're concatenating them with all the chirps that come through the system and are published using Akka distributed pub sub. So this forms the stream of our chirps that we're going to load. And then here, for each chirp, we're doing this map async call, and that's going to invoke this update chirp likes for each chirp. And you can see here, for each chirp, it's going to go to the like service. It's going to invoke it to get the likes for the chirp, and then that returns the list of likers, and then we can update the chirp to have the right number of likers there. So let's say somebody accidentally in the configuration file sets kill equals true, and lagom, which is watching the file system, automatically picks it up, reloads. And so then if we hit refresh here, we can't see our feed anymore. So the like service went down, but because it went down, we can't see our chirps, even though the chirp service is still up. We can see exceptions in the logs here because it was unable to access it. We can see it says that it was killed. Okay, so how do we fix that? Well, setting true equals kill equals false is probably a good start, but more long term, we want to ensure that killing it doesn't cause that problem. So I've done some work already here, just in preparation. Here's our like service interface. This is what a service interface looks like in lagom. You can define multiple service calls, and then you define a descriptor down here which will describe how those service calls are addressed and invoked. So here I've got a counts service call. Service call takes 3 parameters. The first parameter is an ID, and this is something that can be extracted from the URI typically. So we're going to pass in a UUID in the URI. It's optional, and that's going to be the ID of the last of the starting event that we want the counts from, and we'll learn a bit more about that later. Then the request is not used because in this getting the stream we don't need to send a request message. And then the third parameter is the response message, and we're saying the response message is actually an Akka stream source, so it's a stream of messages, and each of those messages will be this likes message. And if we have a look, that's got 3 fields. First a chirp ID, so that's the chirp being liked, then the likes, which is the count of likes, and finally the ID of the event that this is. And that ID is also going to be used in combination with this UUID. So at this point, I'd just like to talk a bit more about why I'm doing this and what I'm doing here. There would be a much easier way to implement this, and that's to use something like Apache Kafka. Apache Kafka gives at least once messaging, and so I can use that to achieve the at least once messaging part of my requirements. I'm not using that for 2 reasons. One is that our integration with Apache Kafka in lagom isn't there yet. It's possible to use if you drop down to lower level APIs, but we're going to provide a really nice API to use that. But that gives me an opportunity to actually show you how at least once messaging gets implemented. And so we're going to have a look this evening. Basically, what we do is exactly the same thing that Kafka itself does. I think that's important to understand, because it's important to understand why your system scales. How is it that Apache Kafka is able to scale out to many nodes, and how is it able to do what it does? So what you'll see me implement this evening is a lot more complex than it needs to be, but it will give you a good understanding of the underlying concepts behind what we're doing. So let's go to the implementation of this counts service call, and you can see it hasn't been implemented yet. Service calls in Lagom generally get implemented using lambdas. So this is a lambda that takes that ID, the offset, and the request, which we're not using, so we're not going to use that parameter. But this offset is going to be what the service that consumes this call, this stream, will keep a track of the ID of the last event that it successfully processed. And so when it fails to, when it needs to reconnect for whatever reason, it can send that ID as the offset, and so then it'll only get the events that happened since then. So the first thing we want to do, we're going to return something immediately, so we just return a completed feature. Then we're going to get the event stream for all the like events. Now, Lagom uses event sourcing out of the box. In contrast to, say, a traditional relational database system where you store your current state in the database. When you use event sourcing, you don't store the current state, you store all the events that occurred. And then by reading those events and having event handlers for those, you can compute the current state. And this has many properties, such as being able to do temporal queries, being able to use a really scalable database because it only has to support one operation, append. But in this case, it's very useful because it means that we can just do a query on the stream of events and be able to present those events to other services. So we're going to get that stream of events. You can see we're asking for all the events from the offset. And then for each event, we're going to have to map it. Now, each event that the like service is storing is something like this user liked this chirp, and this user unliked this chirp, and this user liked this chirp. But what we want to send to the service is the current counts of likes, which obviously from those events can't be determined. So when we get these events, we're going to have to look up the current counts. And so that's why we're doing this map. The 2 there just says we want to do maximum of two lookups at a time. And so for that event, we will go and get the like entity. The like entity is the list of users that liked the event for the chirp. The event itself, the event that's being sent here, the class is actually a pair, and the first element in the pair is the like event, which we can get the chirp ID from. The second element in the pair is the event ID, and that's used for our offset handling. So we're going to ask it for the likes, and then we're going to create a new likes object with a chirp ID, the number of likers, and that event ID. And so we've implemented the like service side of things. Now the chirp service needs to consume that. So in the chirp service, I've done a little bit of work ahead of time. I've added this field, the likes field, to the chirp table. This is actually Cassandra code. I've added this like field to the chirps table, and so whenever we get this likes event, we're going to do this update where we update the number of likes. And at this point, I hope you can see that that this is an idempotent handler here, because if we get an event saying that 10 users liked this chirp, then we'll set it to 10. If we get the same event again, we'll set it to 10 again. Or if we get an event saying that 10 users, and then for some reason we process a whole stack of events again, so we get 8 users, and then as long as they come again in order, 9, 10, we'll end up eventually in the correct state. So that's idempotent event handling. And the reason why that's needed is, you can see here, let's say we execute this right and it succeeds, and then afterwards here we insert the offset into the table. So this is the ID of the event that we last successfully processed. But if that fails, or if the database goes down between those two things, then we're going to have processed an event but not stored the fact that we processed it. And so when we go and load the event streams, we'll end up getting that same event again, and so we'll end up processing it twice, and that's why the idempotency is really important. So I've also added something here to go and get the current likes offset, which we need to start our stream. So in setting up this stream, I'm going to use an actor to do that. This actor, when it starts, is going to make the connection, and it's going to start doing the updates. So the first thing I need to do is get the likes offset, and then I'm going to invoke that count stream on the likes service, passing in the offset. Now when it's complete, when I get the stream back, I could have got an error. It may have failed to get the stream at all, like maybe the service wasn't even there. And so what I'm going to do when that happens is I'm going to fail. Actors, when something goes wrong, the best practice is to simply fail and crash and let your supervisor handle how to deal with that. So we're going to do the supervisor a bit later, but for now we're just going to tell ourselves this failure message, and you can see where we handle this failure message, we're simply throw an exception which will cause the actor to crash. But assuming it's successful, then we're going to take the subscription, the count stream, and for each item we're going to invoke that update chirp likes method that we just implemented. And so now they're handled, and so we can run our stream, but with each message, sorry, not that one, each message we're actually going to feed it into a sync that simply points to ourselves. So by doing that, when the stream itself fails, it will also send this failure message to us and will crash. And so that means if the stream fails, we can then let our supervisor handle that. And this message here is saying this parameter here is what gets sent when the stream finishes gracefully. And again, we're sending the failure to ourselves so that we crash. So, all this crashing, how are we going to handle it? Lagom is built on Play, and Play uses Juice to wire everything together. So if we want to set something up that happens at the start of the application, we have to do that with a Juice module. And so here we're binding our like count subscriber actor as an eager singleton using Juice. So that's going to start it when the application starts up, and we're using a provider to create the actor. When you create an actor, you don't immediately it's not you that creates the actor. You have to let the actor system create the actor, because the actor system is responsible for handling the life cycle. So what you do is you create these props objects which describe how to create the actor, and then you can give that to the actor system, and the actor system will handle that for you. So we're going to create something that describes how to create our like count subscriber. And then we're going to wrap that in a supervisor that's going to do an exponential backoff. And this is where our failure handling happens. So whenever our actor crashes, the backoff supervisor is going to, after 3 seconds, try and restart it. And if that fails, it'll do it after 6 seconds and after 12 seconds. Uses this 0.2, this random jitter. So that means if you'd have multiple actors doing this, they're not all trying to reconnect at the same time. And it limits it to a maximum of 30 seconds. So once it reaches a 30-second reconnect time, it just stays at every 30 seconds. And the final thing we're going to do, we haven't implemented any sort of partitioning of our events. If you use Apache Kafka, it does implement partitioning, but we could have actually implemented it ourselves, where you divide the events up into partitions, and each partition gets then has its own offset. And this would mean that you could subscribe to the stream from multiple nodes. Each node subscribes to a different partition. But because we haven't done that, we've just kept it single, we only want to subscribe to these events from one node because there's no point in having multiple nodes process these events. So consequently, we're using something called the cluster singleton pattern in Scala clustering. It's in Akka clustering, and it's going to ensure that our actor only runs on one node. And so there we have it. The next thing that we need to do is just remove that synchronous call that we had here, because that's now no longer needed. And so if we wait for that to do all the reloading, we can then go back, and the like service is running now, so this should be working. So there's our likes, and we'll see if it works. So I've just liked that. Now I'm going to hit refresh, and you can see it still says 0 likes. Now as it happens, the way that event sourcing works in Akka is it actually, for Cassandra, puts in a 10 seconds delay before it actually propagates the events. And the reason for that is because Cassandra itself may not be consistent. So in order to ensure that all the events come in order, for Cassandra to reach a consistent state, it waits 10 seconds. We probably actually don't need that because of the way that we don't care about two different entities, their events getting out of order, because we're only handling the events on a per entity basis. But I left, you can actually configure that delay to be shorter or even 0, but I left it in there to demonstrate that we're actually doing this asynchronously, because now if I hit refresh, you can see that's now 1 likes. So it's definitely happening asynchronously now. And so, of course, we didn't just do it so that it happened asynchronously. We actually want to implement to see that resiliently. So let's kill our like service. Wait for it to reload. And now, if we hit refresh, you can see that our stream is still working. We can still see our chirps. Of course, our like service is down. We click here, we can't actually see the users that liked it. We try and click like, has no impact. So our like service is down, but our chirp service is still able to respond to our requests to get the chirps. If we actually have a look here, you can see it's that killed message, and our back-off actor has actually tried to reconnect quite a number of times. You can see stream failed restarting there, stream failed restarting. So, just to reiterate again about the about using this, what we've done there, we've just gone and implemented our own at least once messaging. You can see because we're keeping track in the consuming service. It's really quite a simple mechanism of keeping track of that offset. And so we could have used Apache Kafka there, and then all we'd have to do then is on the chirps, publish those events into Kafka from the like service, and the chirp service set up that subscription, and when we provide this in Lagom, it will be literally a 1 line of code change to do that. But what we've seen this evening is exactly how that's basically how Kafka works underneath. The client stores an offset to say what it's processed. So let's move to communicate through the client. Now we're going to look at a really trivial example. The client can cache data. It might cache it for just a small amount of time, just to reduce some of the load, or could cache it for a long time. It might cache it at the start of a session, so that might be minutes, or it could be like a mobile client. If you've ever, say with Twitter, caches avatars, for example, on the mobile client because they don't change that often. The browsers can also cache things. Local storage is a particularly nice way to do that. You can also use a cache as a fallback, so you could try and make the request to the service, but if it fails or if it doesn't return within a given time, then you just fall back to your cache. And one case where we're using synchronous communication where we could replace it with communicating through the client is in the activity feed. So currently we go synchronously to the activity feed, that's fine. But in order to return the chirps, the activity feed has to go to the friend service to know which chirps which friends feeds to get. And then it goes and gets those feeds and returns them to us. So if the friend service goes down, the activity feed can't fulfill its request, and we want to get rid of that. So let's get rid of that call to the activity stream and instead just go directly to the chirp service. So now if the friend service goes down, activity service can't fulfill the request, but that's all right because we're not using it. So just a quick demo of what this looks like. If we kill our friend service, actually I'll just unkill the like service first. Why is that not? Okay, so we can see the feed's still working. So if I go now and kill the friend service, if I go back to the feed, we don't get our chirps anymore. So let's unkill that first. And we can see in our JavaScript here we're using React. There are two different calls to get the stream. One is to go to the chirp service and get the stream, passing a list of user IDs. We currently just pass one user ID when we want to view the stream for one user. And the other is to go to the activity stream for a given user, and that will get the chirps for all the friends of that user. We're going to create a new one that goes to the chirp service and passes all our friends. So we create a new method that takes all the friends' IDs, we do that service call, and then we send the list of user IDs that we want to get their chirps for. And now we can use that in our activity stream page. So we're loading that user and the list of friends for the user from local storage, which we've cached, and then create friend stream with the friend IDs. So let's make sure that's reloaded and recompiled. That looks good. So if we hit refresh here, looks like it's working. Let's now try and kill that friend service again. Wait for a reload. Go to add friend, go back to feed, and we can see we've still got our feed. We're unable to actually load the actual names of the users. We're just getting the user IDs there because the friend service is down, but at least we're still able to read our chirps. So that was a really trivial example. What about something that's a bit more complex? And I didn't implement this because it'd probably be a bit too much to do in a presentation. But another example is client authorization. So I mentioned earlier that requests can go, that if you have, like, let's say an authorization service that we need to go to the friends service, then that can cause a real problem. So what if we communicate the authorization through the client? But how can that be possible? I mean, it's the client that we want to kind of protect our service from. How could, if the client can't just go, hey, I'm allowed to do this, let me do it? Well, the answer is to use authorization tokens, and specifically for something like JSON Web Tokens. So a JSON Web Token is a bit of JSON that then has a signature associated with it. And what that signature, that signature will be signed maybe with a shared secret, maybe with some sort of asymmetric encryption. And so when the user loads, when the browser loads an entity, for example, when it gets the current user, and it'll get the list of the user's friends, that friend service can then send tokens for each friend and say, this user is friends with this user, and here's a signature to prove it. So then when the client needs to do some sort of action, it needs to like a chirp or needs to post a comment or something like that, it's going to send that token with the action, perhaps in a header. And then the service that receives that can say, okay, well, first of all, I'll verify the signature. So I know that this token was produced by the friend service and not just made up by the client. And then this action, this person needs to be friends with this person, and this token is saying that this person is friends with that person, so I'll allow it. And so by doing that, we've now reduced a huge amount of load on our friend service, and we've ensured that our friend service is not going to affect whether whether it's up or down is not going to affect whether the like service is able to accept a like, or whether the chirp service is able to return a chirp. So this evening we've looked at a few different things. First of all, we've learnt that REST, although it's not a bad thing, if we use it just to replace method calls without really thinking, that it can cause some problems. We don't really realise the full value that microservices can bring us. So, and we've looked at two different ways to remove the reliance on synchronous communication. One being denormalizing your data and pushing it, and the other being avoiding synchronous communication by sending things through the client. So as a next step, you could check out Lagom. So lightbend.com/lagom is the current website. It has all the information. There's 4 screencasts on there, as well as a very nice looking video to introduce you to Lagom. Another thing that I really recommend doing is Jonas Bonnier, who's one of the founders of Lightbend and the author of Akka, has written a mini book called Reactive Services Architecture. It's only about 30 pages long, I think, and you can read it in an hour. It's free. If you go to the lightbend.com website /reactive-microservices-architecture, you can get a free copy of this mini book. And it explains everything, a lot of the concepts that I've talked about tonight, plus a lot more. So I really recommend reading that. And if you want to check out this presentation, github.com/jroper/rethinking-rest, you'll find the slides. You'll also find the code branches for the initial state before the presentation and the eventual state. And you'll also find the IntelliJ live templates for doing the live coding. So thank you for having me here, and I'll take questions. Yep.
I got a question. You started up Cassandra?
Yep.
When you started, you're using Cassandra as a cache? Is that the caching mechanism on the server side? You have
No, Cassandra is our data store. It's not being used as a cache. It's the database, and that's what we're encouraging people to use, or that's the default database that we support in Lagom is Cassandra.
Do you cache the results from the client, right? The service, depending on another service, do you cache the results locally?
You could do that, but in the case of the, it's all the chirps are being stored in there. All of our like entities are being stored in there. It's not being used as a cache in this application. It's being used as the database, the data store.
You're not caching from the
No. Actually, we've got some T-shirts. And we're going to give them out to people that ask questions. Where's a light bin person that I can send to fetch them? John. They're just on the bench there. Yep. Do you want a T-shirt? They're all XL. That's all we've got left, unfortunately. But who else wanted to ask? Yep.
So in the case of the caching mechanism, the second point
Yep.
second mechanism, the data that's cached is going to be what was asked for. In the case of the push mechanism, the first one, how do you, were you pushing everything, every like from every user? Was that?
Okay. So the question is, in the pushing scenario, are we pushing everything? Yes, we're pushing every like. I think I'm guessing the more underlying question is, isn't that going to mean that you're pushing a lot of data everywhere and having to store a lot of data everywhere? Is that?
Yeah, because it sounds like the push approach, every node would end up caching
Everything. Yeah.
Whereas with the caching mechanism, it would only
Yes.
be one pass.
So I mentioned that there are many different techniques that can be used to get rid of synchronous communication, and the denormalize and push is one that works in some situations and not others. So in this case, it worked really well because all we had to do was store an extra integer on each chirp. If you wanted to store, for example, if you wanted to store if you wanted to not need to go to the friend service in order to get user information for each chirp, storing, say, the current user's name and link to the avatar or whatever on each chirp, that would be a bit ridiculous because every time they updated it, you'd have to go through and update their entire history of chirps. So you wouldn't use that there. There are other, another approach is to, it may in that case, what you might do, the activity feed is something with a limited number of chirps. So this is, I don't work at Twitter or Facebook, but I'm pretty sure this is what they do to implement the feeds, is they have a materialized view of the of everything that for the past, say, week maybe or 2 weeks, or up to a certain count of tweets or posts. And so there's only a limited amount of data in there. So that can receive the events, and it does make sense sometimes there to put a bit more data there because it doesn't mean that you're going to have to update years of data. So that's another thing, is to create new services that sit in front that hold a view that's just specific to certain use cases at the front. And sometimes it may make sense to have a service that goes and another way would be to actually use caching. So if you had a service that's responsibility was receiving the tweets and getting the user data and caching it, and maybe it might subscribe to updates for the cached user data. There might be some partitioning of things. So, but yeah, there's lots of different ways of implementing these things, and that denormalize and push is one interesting way that will work in many use cases, but not for all. Yep.
Yeah, so this might be a bit outside the scope of your talk, but it kind of relates to managing microservices.
Yep.
So Lightbin has, conductor, right?
Yep.
Discuss the conduction of the microservices architecture. And I'm really curious, where does conductor fit, with respect to container orchestration tools?
With what sort of tools?
Like a container orchestration tool.
Yep.
you have stuff coming out like Marathon and Mesosphere stuff and Kubernetes and Docker. They all have
Yep.
kind of ways of like managing like these processes that you wrap inside containers, these bundled containers. Is Lightbend at all like moving in that direction as well? Of, like,
So,
providing-
so Conductor has integration with a few different container management systems. I understand we're currently adding Mesosphere support. We have integration for Docker and AWS. So Conductor is able to manage a few different things there. So it I guess provides the high level side of things and builds on top of some of those other tools. I think Ed's here. Is Ed? Ed's waving his hand. He's on the Conductor team. So if you've got want a better answer, ask him. Yep.
So compared to the monolith implementation, how much more complex is this sort of implementation in terms of just simple as lines of code and
Yep.
then all the things you have to think about, all the different conditions and all
Yep.
that. And then as the number of services grows, is it like linear or complexity and
Yeah. So the question is, compared to a monolith, how much more complex is this kind of implementation with the microservices, and does it grow linearly or as the system grows? It is definitely more complex than a monolith. Microservices and distributed systems in general are more complex. Now, one of the points in one of Jonas's presentations that he makes is that databases, like relational databases, actually present you a lie. They want you to they present you a view of the world where everything is consistent, which is fine when you don't need to scale and when you don't need resiliency. But as soon as you start to do things across multiple nodes, that becomes a lie, and either you end up with a system that is going to crash all the time, or you end up with a system that can't scale, or both. And you end up you basically can't do the things that you would usually do in a monolith if you want to scale. So yes, it's more complex, but the complexity is necessary, and the key to it is managing that complexity. Now, as far as your system grows, how does that complexity increase? And I'd say when you're using these patterns well, the complexity, I guess, just increases linearly as your system increases. So of course every new component adds that much more complexity. But because all your components are isolated from each other, they don't really add, you're just passing events between them. You're not putting new interfaces where things need to be up things and you don't know what's talking to what. I think as long as you do it right, will help you ensure that complexity stays the same. Where contrast to a monolith, as things start to grow, you start needing to do a lot more caching. You start needing to do clustering. You start needing to worry about things being consistent between those, and things become very complex very quickly without actually gaining the scalability that you need. Yep.
Do you see any interaction then going forward between Lagom and Yakka streams? Or I guess I was particularly thinking in terms of your event sources.
Sorry, was the question, do you
see any connection between this?
any connection between logom and specifically event sourcing in Akka streams. So, so when in the implementation of the Lux service, I asked for the stream of events, and that was an Akka stream. So any streaming that's done in logom is done with Akka streams. So you can get an Akka stream of events directly from your event source database, and logom gives you that. So it's, I mean, there's a very tight connection there, and it's quite a useful use case of Akka streams there. Or was that the question, or?
Yeah, I guess so. I guess I was thinking more from a sort of an analytics point of view, but I guess it's the same pattern, you just implement it.
Yep.
That's a critical part of the request response.
Yes, so I mean, on that same topic, logom provides provides the event sourcing, but to query the data, it uses CQRS. So you then define read source processes, and these are completely separate from your right side event persistence. And so whether that's a read side processor for storing some sort of business data that needs to be returned to the client, or whether it's going out to some sort of analytics, you know, putting a data store somewhere, maybe then to be processed by Spark it doesn't really matter. It is completely disconnected from the events coming in and being persisted and that state being updated. So, that side of it, you don't really need to see Akka streams there, because logom currently provides a fairly opinionated API, which is more specifically designed for CQRS than Akka streams is. But of course, you could do exactly what I did there with publishing those likes to expose that events as a stream if you wanted to process them in another service for sure. Yep.
Actually, I have two questions. So
Yep.
First one is, so in REST, one thing that everybody used to do is, or still do, is service versioning. As your database grows and our business understanding changes, you need to change your data model and you change your endpoints.
Yep.
Assume you have to version events as well. So, like, what are the practices around event versioning or replay capabilities and this kind of thing? Because in REST endpoints, you can keep a backward compatibility. The nets eventually learn how to use the new version. But with events, because it's a push model, like the new events will arrive. So it may be the case where the event processors or injection is not even prepared to read that yet, or can read that wrong. So, like, I want to hear more about that.
So the question is, in a REST system, you often use versioning because things might change, but in a push system, because you're just receiving the events, you're not requesting a specific version, and so how do you handle when things change? So just back to using versioning in REST, the first rule of, we've had a number of discussions this in Lightbend and how this should pan out, especially in microservices where you're going to have many services that now have may need to deal with multiple versions. The first rule of versioning APIs is don't version APIs. So first of all, don't break things. Ensure that all your changes are backwards compatible. Okay, but sometimes that's not enough. So the second rule of versioning APIs is don't version APIs. So sometimes, and you can prepare for that by ensuring that you design your schema to be forwards compatible. And so a good example of that is if you have a list of things and let's say it's a list of strings, don't do that. Do a list of objects. And even if they just got a single string property, at some point in future, it's a very common thing when you've got a list of strings to sometime later turn it into, you need more information for each item in that list. And if it's a list of objects, then you can always add more properties later, whereas if it's strings, you can't do that. But of course, sometimes you don't foresee these things, and so you really do need to change your schema. So the third rule of versioning APIs is don't version your APIs. What you really want to do is, if the protocol changes, you create a new service to handle that new protocol. And so then services that want to speak the old protocol speak to the old service. Services that want to speak to the new protocol speak to the new service. The old service, you may have it mapping, you may have one of them just being a facade over the other one and mapping each other like that, but they do need to be separate services. Now in Lagom, we haven't implemented this yet, but we will be providing support where we'll do some of that mapping automatically. So you can define, migrations, I guess, from the old protocol to the new protocol when that's possible. But conceptually, it's still important to see these are two different services. They speak a different protocol. When it comes to push, it's essentially the same thing. So if in the case we were doing a peer-to-peer push, and what we were doing was we were connecting to this service. When we connected to it, we could connect to a different version of the protocol. If you're doing a publish-subscribe sort of thing, what you would do is you'd publish to a different topic. So there's one topic which is for the new protocol and one topic which is for the old protocol. And you might, in order to implement that, have a subscriber to the new protocol that translates it to the old protocol, and so the old consumers can still consume that old topic, the topic for the old protocol. But conceptually, I think the best way to view it is we don't actually have versions. We have a service speaks a protocol, and it ensures that all the changes are backwards compatible, and when we have a new version, it becomes a whole new protocol with conceptually a new service. Yep.
Say we have some existing services implemented on using the
Yep.
existing legacy services, and we are actually going to introduce some new services. So how can these two actually coexist?
Typically, so the question is, how can two services how can the new service coexist with the old, especially if the old is a legacy one which hasn't been versioned? What you would have is different service names. So put the version in your service name, and if the old one doesn't have the version number in it, that doesn't matter because the new one does. So in Lagom, when two services talk to each other, they look up in the service locator for the service name that will give them the IP address or the URI for that service, and they'll be able to talk to each other. It gets a bit more complex if you're going through a gateway, because then you might have to do some versioning via headers, or some things where some things put a version in their URI and others don't. Again, if you're for the outside world, it's then even more important that you don't break things, because you have no control over the outside world and who's talking into you. So really, back to rule one: don't version things.
Yeah.
Yep.
Say I'm trying to reproduce some new services, but I have some existing other people.
Oh, not using Lagom, you mean?
Exactly.
Okay, sorry, I thought you were asking a different question. So for Lagom itself, there's actually something that I put into the Lagom documentation, which was a little controversial when a few people first saw it, and I said, if you have a big system with many services and they're all Lagom services, then you possibly should be rethinking how you're making your technology choices. Because one of the big advantages of microservices is that you can choose the right tool for the job. And Lagom is a great general purpose tool, but there are going to be some jobs that you have where this specific tool over here that isn't Lagom is going to fit the purpose better. So in Lagom, there are a few things we are doing to ensure that it enables you to have a polyglot stack. One thing that we're doing is we ensure that we only use standard protocols everywhere. So when we do REST in Lagom, it is idiomatic REST. It is REST the way that everyone does REST, not Lagom's brand of REST. When we do the streaming, we're using WebSockets. Again, that's a standard protocol. And we're also going to be introducing support for generating Swagger specs and generating clients from Swagger specs. So Swagger is a specification for a remote interface that has a fair bit of support in different stacks. And on the deployment side of things and the development environment side of things, we are having ways of, if you've got a system outside of Lagom that's not deployed to, say, Conductor, I've been able to tell Conductor, hey, here's this system, so when this client needs to talk about it, you go out over there outside of Lagom to talk about it, to talk to it. Being able to integrate with legacy systems, with non-Lagom systems, with systems that just don't fit in for whatever reason is a very important thing in microservices, and something that we will are providing support for. Anyone else? Well, thank you.